Hi everyone. In this video we talk about how the symmetric groups are related to symmetries of regular polygons. So we'll be considering the rigid symmetries of regular polygons. This will include certain rotations and reflections and combinations thereof. It turns out that these symmetries form a group which we call the dihedral group, D sub n, where n represents the number of sides in our regular polygon. We're going to be seeing that this dihedral group, D sub n, can be regarded naturally as a subgroup of the symmetric group, Sn. We begin with the dihedral group D3. So D3 is the symmetries of an equilateral triangle. And that should sound familiar because in the last video we talked about the symmetries of the equilateral triangle. And we saw that those symmetries are really just the symmetric group, S3. Right, so in this particular instance, D3 and S3 are identical. And now, to remind you of that situation, remember we had a triangle, equilateral triangle, say in what we would call home position, where we're going to label the corners of the triangle 1, 2, 3, and then they have positions which are fixed once and for all, 1, 2, 3. And then what we might do is take that triangle, pick it up, and do something with it, like rotate it or flip it. For instance, suppose we decide to rotate it clockwise by 180 degrees and put it down again. Well, the positions are fixed, but the labels on the triangle have now moved, right? The 1 is there, the 3 is there, and the 2 is there. So this is a 120 degree clockwise rotation. And that corresponds to the permutation that looks like this, where the domain are the labels on the triangle and the range is the positions. So here, label 1 now is in position 3. Label 2 is in position 1, and label 3 is in position 2. Now you might remember last time we saw a simpler way of writing permutations like this. So instead of using this array with 2 rows, we're going to just write this in cycle notation. Right? So this as a cycle is 1, 3, 2. So whenever you see a permutation like this and it corresponds to a symmetry of a figure, you can think of the input as being the label on a corner of the figure and the output as its corresponding position. Okay, so we can take a rotation like this, or, for instance, the other rotation, which would be 1, 2, 3. In fact, let's use that one. We're going to call it F. So this is 1, 2, 3. And we're going to let G be the reflection across the vertical midline, which, remember, just fixes 1, but swaps 2 and 3. Right, so this is what I've written here is not correct. So really it fixes 1 and it swaps 2 and 3. So if we let F be this rotation and a G be this flip, what we can see is that D3 turns out to be this collection of things. So it's the identity, it's the 120 degree counterclockwise rotation, it's the 120 degree counterclockwise rotation composed with itself, which is just the 120 clockwise rotation. And then it's this flip, and then there are these other things that are in there too, FG and F squared G. So I think it would be a good exercise for you to make sure that these products, or compute those products explicitly, and make sure that this set really does give us all of S3. Now, one other thing that I want us to look at here and observe is that this S3 or D3, both, either one, because they're equivalent, they essentially have generators, F and G. So F and G are primary movers here that give rise to the whole group. So that's the first thing. The second thing is that if I take the order of F, that's going to be 3, and the order of G is 2. And then F and G interact in this way. That is, if I take FG, that's the same as taking G times F squared. And this latter observation is rather important because it tells us if someone were to hand me a jumble of F's and G's and were to tell me to multiply them together, this would give me a way of moving all of the F's past the G's. For instance, let's take this and compute a product. I don't know, let's take, say, G times F squared G times F, and see what that should be. Well, I know that GF squared is the same as FG, so I'm going to take this GF squared and replace it by FG. And I know that the order of G is 2, so when I take G times G, I'm going to get the identity. So this is just F times F, which would be F squared. Okay, so that is the structure of the dihedral group D3. Next we address D4, which is the symmetries of the square. Now, unlike D3, D4 is not going to be all of S4. So let's take a look at the things that will lie in D4. So we're going to take a look at a square here. And it'll have home positions 1, 2, 3, and 4 that will stay the same always. And then we're going to label the corners. And these labels are movable depending on how we move the square. So one thing we could do with this square would be, for instance, to reflect across a vertical midline. So this is going to be a reflection across a vertical midline. And if we do that, we would see that 1 and 3 would be fixed, and 2 and 4 would be swapped. So if we try and draw that out here, all right, so our positions stay put. 1 and 3 stay put because we're reflecting across the vertical midline, but now the labels, label 4 is in position 2 and label 2 is in position 4. And so that permutation does what? Well, you can think of the top row as being the labels that we've put in the square, and the bottom row as being the positions that those labels go to. So 1 and 3 retain their positions, but 2 and 4 swap their positions. So that can be written more simply just as the transposition 2, 4. All right, so there are other sorts of reflections that we could do. For instance, we could reflect across a horizontal midline, or we could cut the square like this, or we could cut the square like that. So that accounts for 4 types of reflections. And then there are these rotations, right? We could rotate by 90 or 180 or 270, or we could do nothing. That accounts essentially for 8 operations. Okay, now how can we sort of efficiently write down all of these elements of D4? Well, you can break the elements into rotations and reflections. So let's let G be the reflection that we've already come up with. Right, so that's going to be 2, 4. Sort of the reflection sort of across the midline. And then why don't we let F be a rotation? Right, say this cycle, 1, 2, 3, 4. Now remember, in all of these, you can think about the input as being a label and the output as being its final position. So here, if you rotate counterclockwise 90 degrees, label 1 will go to position 2, label 2 will go to position 3, etc. So this is our sort of reflection across the midline. This is a 90-degree rotation. And in fact, it goes this way, right? And it turns out that D4, that is, all of these symmetries, can be expressed in terms of F and G. So you get first all of these rotations. So E is the do-nothing operation. Then we get F and F squared, which is 180, and F cubed, which is 270. And then we get G, which is our reflection, and then we can multiply G by these various powers of F. Right, so that's F cubed times G. So some things to notice, right? The order of G is 2. Right, G times itself is the identity. The order of F, in this case, is 4. Right, because we have to apply the rotation 4 times to get around to the identity. Now, what do you do if you have a whole bunch of F's together with a whole bunch of G's and you want to return to one of these symmetries that we've listed, these 8 symmetries? Well, you need to know how F and a G interact with each other. So it turns out that if you take F times G, that's the same thing as G times F cubed. And this allows you to compute products of, crazy combinations of F's and G's and wind up with something that sits within that list. So this type of analysis, it holds for all regular polygons. And in fact, if you look at the dihedral group Dn, where n is the number of sides in your regular polygon, turns out that that is going to be a group of size 2 times n, and it will be generated by an element F, which is a rotation, and its powers, which will be larger rotations, and these reflections. So those will be the rotations, those will be the reflections. Where F is a cycle, like 1, 2, up through n. And G here, I've not written it as a product of cycles or anything like that. I think it's easier to see it this way. this G is a reflection across the vertical midline. So, all of these dihedral groups are generated by F and G, where F has order n, G has order 2, F is a rotation, G is a reflection. And, of course, there's this relationship between F and G that allows you to take some giant jumble of F's and G's, multiply them together, and be able to slide all the F's to one side and all the G's to the other.